and then sharing my desktop. Okay, should be visible, right?
Yes, sir.
Okay.
Yes, sir.
Okay. Okay, so today and the next week, we will cover the remaining things about Bash. So let us first look at some simple things about Bash. Next, and then we will start how to program Bash. Okay. So what we have seen so far in the last week is how we can deal with variables, arrays, associative arrays, and I would say arithmetic operations. Okay. Integer arithmetic and also floating point arithmetic. Now, another fundamental, I would say, building block in a shell program is a function. You can have user-defined functions. There are also some functions defined by the system, the initialization thing, but you can also define your own functions. And this is how you can do it. Just write the keyword function. Actually, this is not necessary. You can avoid this. So give some name following the naming conventions, which are similar to as in C, and then with or without space, opening parenthesis, closed parenthesis, and then within a pair of curly brackets, you write whatever comments you want to have your function to execute. Okay. So this function is not necessary because even without this keyword function, this syntax says that you are defining a function, so you can avoid this function. Okay, that is only optional, or if you give it, it's not a problem. In fact, it makes things more, a little bit more readable. Okay, so after you have defined a function like this, okay, this f name is now become a command. Okay, so you can call f name argument 1, argument 2, argument 3, and so on. Okay, and inside this function, there are some default shell variables, right? Dollar star, dollar hash, $1, $2. These refer to command line arguments. Okay. So if you remember, $1 is the first argument, $2 is the second argument, dollar hash is the number of arguments, dollar hash is all the arguments taken together as a single string. And the function can also return certain values. Okay, maybe return thing will come little later. Okay. And if you want to see which functions are defined in the current invocation of this shell, you can simply write declare minus f. There you will see a lot of functions and their definitions. Okay. And you can unset a function, that is basically deleting a function. And shell functions can be recursive or mutually recursive, things like that. And there is one particular default shell variable called funcnest that can be set to a positive integer to limit the recursion rates. Okay. Otherwise, if you do not set it, this is basically infinity. And therefore, you may have the function calling itself, calling itself, calling itself, calling itself. And if that happens for a huge number of days, then essentially your, I would say, your window or whatever your application will hang. Okay. So if you have a premonition or hunch that this may lead to infinite recursion depth, set funcnest, nesting. How many? Nesting. Okay. So that after this limit is reached, there will no longer be any further recursive calls or function call. Recursion depth or call depth. Okay. So let us look at some example. Okay. So let's define a function to power. Okay. It starts by echoing to power exponent. Okay. This is the usage. Then it says 2 to the power $1. So $1 is the first argument that we specify. Is dollar within this? So this is the exponentiation operator. 2 to the power $1. Okay, so I mentioned to you in the last class that within this, I would say, pair of parentheses, you enclose one arithmetic expression, and there you can actually avoid using this dollar, but here this dollar is mandatory because if you remove this dollar, it is 2 power 1. Okay, so use dollar only when it's necessary. Otherwise, it's only optional. Okay, 2 to the power $1. So here is the next example, 2 power 10. So 2 power 10 is 1024. 2 power 30 is this. 2 power 60 is this. But if you say 2 power 100, you get 0. That happens because in at least my version of Bash, these arithmetics are 64-bit integers. Beyond that, there is overflow, and therefore you are saying 0.
Sir,
Okay. Yeah, tell.
sir, how did you write the second and third lines? I don't understand how it's written inside the function.
What is the question precisely? So I'm saying this is a function. Okay. And then I am doing this opening brace or curly bracket. And these prompts that you see, this is the secondary prompt, PS2, to be more precise. Okay, so this is what I did not write. It's greater than
Yes,
sign.
sir, that was what I asked.
Yeah. This is what I did not write myself.
Yes, sir. So can you please explain a bit? I don't understand.
No. Dollar is the primary prompt.
Yes, sir.
Okay. But since Bash knows that until it sees this matching closing brace, the definition of the function is not yet over. So until it sees this brace, it will keep on issuing this secondary prompt, greater than, greater than, greater
Okay,
than.
okay. So,
Okay.
and why are we writing echo?
This thing you simply type.
That's fine, but why are we writing echo? Why are we using echo? I'm asking.
Echo will echo this thing.
So what if we write only usage colon 2 power
So
exponent?
then this becomes a command.
Oh, okay, okay, got it.
Okay. Yeah. Now the command is echo. Okay. Fine.
Sir,
Yeah. Well,
sir, why you have written two brackets?
this is for arithmetic expressions. You recall? Arithmetic expressions are evaluated this way. Dollar, double parenthesis, and then inside it you put your expression. This is the syntax for doing arithmetic operations, but only integer. Okay. Happy or not?
Yes, sir.
Yes.
Okay. And this is 0 because of an overflow. And then if you say to power without any argument, then $1 is basically empty, undefined. Therefore, if you raise 2 to the power something undefined, and this Bash will say syntax error, operand expected. Okay. Likewise, if you say -3 to power -3, this cannot compute. Okay, so exponent less than 0, error token is 3 or whatever. Okay. So this is how you can define a function. Now you will ask a question. A function can also return something. The big question that I now raise is that whether I should use this return statement to return a value or not. Okay. The simple answer is not. No, do not do it. The reason is this: inside your main function in a C program, you can return a value or exit something, an integer, small integer value you can pass to exit, right? Now, this return value from your C program or this function is not really treated like a return value, the result of a computation. Okay. Instead, it is usually treated by bash by the exit status of this command. So the returning is for returning the exit status. Okay. And that is usually a small integer, like unsigned 8-bit integer value. This can be returned. You can treat it as a return value, but when you do shell programming or you deal with shells, this return value should not be taken in the usual sense. Okay, the return value is treated as an indicator of successful completion. 0 means success, anything non-zero means anything non-zero means failure. This command failed for some reason. Okay. And what type of failure it is, that can be given by the status. Okay. For example, in your C program, if it is a normal termination, you can say exit 0. And if it's some abnormal termination, like some file name is not found, some value, some pointer is empty, then you can return exit 1, exit 2, exit 3, depending upon what type of error you face. Okay. And here also you can do a very similar thing. So if I use it as a return value, okay, this is basically allow $2 raised to the power $1. Okay. But then this quantity 2 power something, this is basically returned as the status. Okay. And the status is available in this default variable $? Do you remember this? $?
Variable which is not given a value.
Yes, yes.
Any variable that's not given a value.
Any variable that is not given a value. No. $? Is whenever you run a command. So after you define the function becomes a command. So whatever its exist status is, that is stored in the variable default variable $? Okay. So you can now use that return value, return status actually, to set some value, red val, and then you can use it in any manner you want. You can echo $return value. It becomes 4. So 2 power 7 return value equal to $? Echo it. It's 128. But the moment you, increase the argument to something beyond 7, 8. It's only an 8-bit unsigned value. The maximum thing that it can store is 255. 2 power 8 is just bigger than that. So this is basically an overflow, case an overflow. Okay. And so return value actually gets the value 0. So up to 2 power 7 it is possible. And it is not advised that you use this return statement to return a value. Okay. It is to be used as a status instead of a return value. But then how do I return a value? One possibility is you can set a non-local variable, okay, instead of return. So here, for example, I am just setting the value return val red val equal to $base, this quantity, this result of this arithmetic expression. And since this is a global variable, you can set it to big things, like 2 power 8, return value is 256, 2 power 50, return value now becomes this. But if you say to power -3, there is an error in evaluating this expression, and therefore this is not done, and return value is not assigned anything. So the old value remains. So therefore, echo return value will say this old value. Okay, so this is one way of returning results of computation. It is always preferable to return using this return statement, because this return statement is meant for returning a status, not the result of a computation. Keep it in mind. Okay.
Sir, how far can we go with this? I mean, how large an integer can be stored?
64-bit.
Okay.
This is
And sir, suppose that we want to come out of the whenever we write that function and give a open brace so that it goes into an angular brackets, right? So how do we come out of it? Suppose that I've written something wrong there and I want to come out of it.
Oh, Control C. I think Control C will work.
Sir, I didn't get you.
Control C.
Okay.
I think Control C will work. Or otherwise, just close the bracket. Okay. Possibly nothing will happen. Because function is defined, but it is not called, and therefore until you call the function, whether there is any syntax error and all that stuff, this is not perhaps checked. Okay, so this bash or whatever, this is an interpreter. This is not a compiler. The moment you enter a function, it does not compile it. It keeps it as a string. Okay. But anyway, I think Control C will work. We'll check it out. Okay. So now a little bit I want to say about variable scoping.
Yes, sir. Works.
Yeah, Control C works, right? Yes. Okay. Fine. Okay. So in case of Gawk or awk, you have seen there are as such no local variables. So we are using some function parameters as local variables because that is the only way of doing things. But in a shell, you can declare local variables. Okay. So the keyword is local. Local followed by a variable name. We'll say that this variable, even if it is defined globally or in some outer scope, is treated locally in this invocation of the function. And not only in this invocation of the function, in all functions or that is called from this function. Okay. So a local variable shadows a variable with the same name in the outer scope, if there is any. Okay. And a nested function call sends global and all these local variables to the called functions. So these local variables does not mean they are defined only inside this function. If I make another function call, from this function call, these local variables will also go there. So that is unlike C. If you have a global variable, a local variable int I somewhere, and you make a call my function, the value of I will not go there, right? Unless you pass it as a variable, as a parameter. Okay. But here, if you declare a local variable I and make a function called myfunc, then this value of I will be accessed inside that nested function call. Okay. And the innermost scope where a variable is defined is used. Okay, so here are a few examples. You can work it out. X is 3, Y is 4, Z is 5. You are assigning these three variables globally. And then you are calling fx, defining fx. Here you define x as a local value, local variable, and initializing it to 6. And then let us see what value x, y, and z and w gets. Okay. So fx is x equal to 6, y equal to 4. Okay, x is defined as 3 here, but inside this function fx, x has an inner scope, which is defined as 6. So this is 6, y equal to 4, z equal to 5. W is, as of now, not defined. right? Therefore, it will be empty. Okay. So this says that the scope of x changes inside this function fx. Okay. Now let us look at another function fxy, where y is treated as a local variable and is given the value 7. W is treated as a local variable given the value 8. X is also treated as a local variable. Okay, and is given the value 9. And inside this, you make another nested call fx. Okay, and then you call fxy. So y gets 7, w gets 8, x gets 9. Then you go here. X now is defined 3 times. X equal to 3 here as a local variable, x equal to 9 here, and here as a local variable, it is defined as 6. So 6 will be printed. Okay. Y is a local thing here. It has the value 7. In the outer scope, it has the value 4. When you make this call fx, there is no local variable called y, but the innermost definition of y is 7, so 7 is printed. Z is 5 as usual. And here, w is declared as a local variable. Therefore, when you call fx from inside this function, this w will go to this fx. So now it will print w equal to 8. But once you come out of fxy, once again you call fx, w is still undefined. Understand? This is fine, right?
Yes, sir.
Okay. So if I now define another function fxyw, where y is treated as a local variable, and w is not a local variable, but I use w equal to 8, and then if I call fx, it will come here, it will get the value of w equal to 8, so it will print 8. But here w is not a local variable. It is a global variable, so w is now set to 8. It is no longer undefined. So when you now call fx, you will see 6, 4, 5, 8. Okay, and also you can see it from the outermost thing. X is 3, y is 4, z is 5, and w is 8. So w is set as a global value in the function fxyw. Okay, so this is the scoping issues, and you can use local variables unlike awk, where there is a very peculiar way of using local variables. Okay, actually you see that although I have written the semicolon here, semicolon here, semicolon here, this is just because we are very used to C kind of coding. Okay, this last semicolon is not needed because semicolon is a separator, not a delimiter, unlike in C. Okay, anyway, if you write it, it essentially means there is a null comment after this, so it doesn't matter. Okay, so now there are some issues not very relevant for the moment for the rest of this shell programming thing. So you just read these things. Okay. Unix processes. I have given a very brief overview of processes. Okay. And how these processes are organized in Unix. Okay. It's something like a process tree. And this we eventually have to understand when you study operating systems. Okay, because you have to create your own processes. There is a command called fork, and your new processes will run certain things. So you have to use something called exec family of system calls. Okay. At that point of time, this process tree will be useful, but you just go through these slides to know how these processes are organized in Unix. This is also something I want to avoid. You can just go ahead and read what is aliasing. Yeah. This is the last thing I will cover in this set of slides. Okay. Now, Bash has something called wildcards. These are like regular expressions, but not as powerful as regular expressions. Okay. There are only a very few primitives. Okay. What Bash does, if you say ls star dot star, okay, it will try to find out which of the files match this star dot star, this pattern. And if this is file1.txt, file2.c, file3.pdf, okay, all the matches it will replace that those all the matches will replace star dot star. Okay, so this behavior you should understand. And of course, if you use quoting, single quoting or double quoting, then there will be no substitution. Okay, so these are the patterns. Star is match any string. Question mark match a single character. And within a pair of what is that called? Brackets, square brackets. Okay. You can supply a range. And the range may be something like A to Z, A to G, 0 to 5. Okay. This is similar to what you saw in connection with regular expressions. Or there are certain special things like special range, like alpha standing for alphabetic characters, digits standing for digits, alphanumeric, uppercase, lowercase, blank, space, hexadecimal digit, and so on. Okay, so let us see some examples. Okay, so start.txt matches any file with the extension .txt. Dot star matches. Okay, so what is called all hidden files. In Unix, any file or directory whose name starts with a dot is called a hidden file. If you use a directory listing like ls directory name, then the files that start with dot are not listed. Okay, if you want to see those, you have to run this ls as ls minus a. Okay, all, A stands for all, dot star. Not dot star, that directory. Okay. And this question mark .txt matches any file with a single letter name with an extension of .txt. It's like a.txt, b.txt, c.txt. And question mark, star. So 3 characters must be there, then this is followed by anything. So this matches any file with the name having at least 3 characters and with an extension of .txt. Okay. 0 to 9 star matches any file starting with a digit. And also you can use this thing, alpha digit start.jpg. So matches any JPEG file whose name starts with an alphabetic letter followed by a digit. Okay, and so on.
Sir.
Yeah.
Sir, how do we differentiate between hidden files and directories? By the name, I mean.
Yeah, if the name starts with dot.
For both, right? For directories as well as hidden files.
Yes.
So how do we know which is directory?
Oh, when you make this long listing with look at that initial thing, RWX, those things. Before that, there is something called D. Do you remember?
No, sir.
Oh, yes, then let's do it. ls
Okay,
minus L, directories will have D at the beginning. Non-directories, that is the other regular files, will have just minus there.
Okay, okay, got it.
Okay. And if you run this with ls minus capital F or ls minus p, then it will append a forward slash after the name of the directories. And if it is just a single file, it will not append that forward slash. Anyway, so there are multiple ways in which you can distinguish a directory from a file. Okay. And here are some programming examples. So let's say SPL has these things. Okay. This is the plain thing, ls minus p SPL. Okay, so now your question is answered. Minus p actually appends this to subdirectories, to directories. Okay. So by this format, you can see this is a directory, this is a directory, this is not a directory, this is not a directory, this is a directory, and so on. Okay. And if I say ls minus p SPL by start.txt, what shell will do, shell will go to this and find all the files with extension .txt. So this will be this one and this one. So before calling ls minus p, it will simply substitute these things. SPL by books.txt followed by SPL by syllabus.txt. Then it will call ls minus p. So this substitution is done by bash. Not by ls. This is the thing you should understand. There are two programs running here, right? One is the interpreter bash, another one is this ls. This is also another command. Built in or not, whatever, it doesn't matter. It is maybe somewhere there, somewhere not there, but there are two persons involved here, the bash and ls. The substitution is done by bash, not by ls. After this substitution, everything, whatever argument 1, argument 2, argument 3, whatever matches, this thing will go to ls and it will individually list them. Agree? Yes, yes.
Sir, what substitution is taking place?
What? Okay. What is the substitution case here? Okay. So how many of these files match here? This one matches. This one matches. No other file matches. Okay. So what bash will do, it will replace this quantity by SPL by books.txt space SPL by syllabus.txt. And then it will call ls minus p. So the effect of this is ls minus p SPL by books.txt space SPL by syllabus.txt. Is it clear? Okay, and as I mentioned,
No, sir, I did not understand this.
You do not understand. Now let's say I have quoted this. Okay. Then what bash will do, it will not expand this star. So as it is, it will go to ls. So ls will get the first argument as minus p and the second argument as sl by start.txt. So it will take that star literally and will try to find a file with the name start.txt. It will not find it. So it will say you cannot access this. No such file until. Okay. So the star is not understood by ls. It is understood by the command interpreter bash. Okay. So think of this as a preprocessor before actually making this call. So file 1 matches this, file 2 matches this, file 3 matches this. Let's say 3 files matches this, 3 files match this wildcard. Then what bash will do, ls minus p file 1, file 2, file 3. It will literally substitute all the matches one by one and make substitution 1 space substitution 2 space substitution c, and then it will call this ls minus p. Still not clear?
Yes, sir. Now it is clear.
Okay. So the star is handled by the shell, not by the command that you are calling. You can see ls cannot handle star. It takes it literally and tries to find a file called start.txt. But there is no such file or directory, so you just cannot access this. Okay. Instead of making this call, you can also say, assign a thing like this, SPL text equal to SPL by start.txt. And then you simply ls, or you can even echo this. Okay. And you will see this and this. Okay, but once again, if you quote it, double quoting will evaluate this variable. Single quoting will not even evaluate this dollar. Double quoting will evaluate this, but that evaluates to SPL by start.txt. Okay. But no further thing. So ls will be called on that. And once again, ls will fail because it takes star literally. Okay, and so on. Okay, all these examples are like this. For example, this quantity, this is a variable you are defining, and the value is this. And if you say $this, this will evaluate to this ls minus pspl by start.txt. That will be run as a command. And since this is not quoted, okay, this will be expanded by the shell. Okay, so you can use it, you can never use it, but sometimes it is a good feature. But don't forget this thing. The substitution is done by the shell. Okay, all the matches that are found are listed one after another, separated by space. Actually separated by the internal field separator, IFS. Okay. Okay, so these are basically, I would say, yeah. Any questions?
No, sir.
Okay, possibly no. Okay, so these are the basic, I would say, shell features which you should understand. After this, we will now go to shell programming. Okay, so you now know the shell to some extent, but you can now define functions, handle variables, arrays, do arithmetic expressions. So these are some basic things. Okay. Now what remains, how you can do some kind of conditional execution, if then else kind of stuff, or for that matter, how you can loop. So this is part of the programming of the shell. Okay. So this thing we will now start studying. Oh, this is Control Shift P. Okay. So how you can use Bash as a programming language? Okay. But then, of course, the first question that arises, why should I use shell programming? Given that I have C, given that I have Gawk, why do I need to use shell as a programming tool? Okay, that's an obvious question. Okay. The idea is this. There is some scope where the shell programming actually wins. Okay. Definitely, and in some sense, in Turing computability sense, you can write C, C++, Java, Python, or awk programs for every doable thing. Okay, if that can be done, you can write a C code for it. But awk already demonstrates that when it comes to the case of handling database input files, you can write awk codes compared to C codes doing the same thing. That awk code may be just 10% of the size. After this awk assignment, I hope you will agree to this. Definitely, you can write a C program for whatever awk assignment we have given to you.
Sir,
But the
we
awk
can't
code is
use
something like, yes.
Sir, but we can't use Valgrind or GDB here. I mean, it was a lot of pain to debug it.
I think awk and all this stuff also have some kind of debugger. Even shell programs have a debugger. Okay. There is a way of doing it, which I do not fully remember now. True. That is true. For C, you have a lot of tools. And but at the same time, you should understand that awk or a shell does not allow you to do some kind of user-defined memory management. Right? So there is nothing called malloc and then forgetting to free. Those things are very specific to C or C++ programs. Okay. So possibly Valgrind and other things, these are not that applicable to shell programs or awk programs. But anyway, there are applications where if you use the awk programming language instead of C, you can save a lot of lines of code. Your programming becomes simpler. Right? So the awk assignment which we have given, just imagine that you are writing that in C. It will be a huger code, right? 2-3 times at least larger than your awk code. Do you agree or not?
Yes, sir.
Okay. So here also, there are such scopes where writing a C or C++ or Java or awk code will actually have many lines, whereas the shell can do the same thing. Okay, certain specific kinds of things in a much simpler way. Definitely, you will not perhaps write a shell program for computing Fibonacci numbers, although we will do it for demonstrating concepts. Okay. And of course, you know that you have precompiled libraries in C, C++. Okay. Make your job easier. You do not have to write the library for everything. For square root, graph libraries, you can use many things. And C programs have, I would say, their own domains of application, like number crunching, data structuring. Okay. But there are certain special tasks, okay, that C programs can definitely do. But if some special programs are there, which are essentially designed to do these special tasks, then their programming effort may be much less. Okay. For example, grep specializes in pattern matching. Definitely, grep is most likely written in C. So you can write your own pattern matching code or use some library. Okay. But then if you just call grep, give a pattern, give the file names, you actually save a lot of programming. Okay. Gawk specializes in text data processing, and a shell like Bash specializes in some specific types of applications. This is mostly related to file handling. Okay. Okay, so that's what I'm mentioning. C programs for these special jobs are often huge and difficult to write. Okay. And the idea about shell is that shell script is an all-in-one solution to simplify a programmer's life. Okay. First of all, do let the shell program do whatever it is good at. And then, if you have a number crunching or data structuring operation, write a C program and simply run it as a command from your shell script. Or if you want to use some other special, I would say, software or special piece of command like grep or bomb, simply call them from the shell. Shell supports this. Okay. Of course, again, if you write a C program and use that exec family of, I would say, system call, you can run anything from your C program. But again, you have to write something like 4, 5, 6 lines. Whereas it is extremely straightforward. You just call the function. Okay. So let the shell do whatever it is naturally good at. And for special tasks, simply call the specialists. It may be your error or grep or gawk or other specialist. Okay, in that sense, the shell script is an all-in-one solution to simplify a programmer's life. Okay. But then I would say the shell script is mostly relevant for what is called system administration. Okay. Of course, it has other applicability areas, but for system administration, these shell scripts are very, very useful. Okay. Anyway, we will not have time to look at some system administration issues. In any case, this slide gives you an idea why we should do shell programming. Okay. It is just for your convenience. Okay, so I hope you are motivated somewhat, I would say, because unless you grow some experience in shell programming, you will perhaps not understand what I am talking about. Okay, but that requires time for you to get acquainted with. Okay, so what you have already seen, how Bash can execute commands, manage variables and arrays, define functions, do arithmetic expressions, and store the complete output, not the return values produced by other programs using backquotes or this $single parenthesis, okay, and so on. And some kind of wildcard substitutions in command line. Now, what remains for you to know is the control structure. So that starts with condition checking, okay, then conditional execution like if then else, and finally looping, okay, for loops, while loops, and so on. Okay, so this thing you already have seen. The rest of this set of slides is devoted to these remaining issues. Okay. But before going there, let us see some simple examples of shell scripts. Okay. Maybe like your initial first C program, let us write a hello world script. Okay. And possibly you have used that thing, right? Hashbang user bin awk -f. You have used that, right? You're supposed to have used that. You're supposed to use that for this assignment. Okay. So on the first line, you simply say hash followed by this exclamation mark or called bang, and then whatever interpreter you use. Okay. And then one by one you write your shell commands. Okay. Add execute permission to that script, then simply run. Okay, so here is a simple example. On the first line, in my machine, bash is in bin bash. It is also in user bin bash, but I think these are just some kind of hard links. Anyway, I don't know. Whatever. This is the name of the interpreter. Hash bang means run this. Whatever follows will be interpreted by this interpreter. I will simply say echo hello world. Then change mode 755 hello.sh. Then you simply run /hello.sh. It will simply echo this and the comment and this prompt returns. Happy or not? This is fine, right? But even for writing this small thing, I think a C function will even be a little bigger. 4 or 5 lines you have to write, right? Even for this hello world program.
Yes, sir.
Okay. Now, this is an example of using a shell script. Okay. And I want to recursively find all the files inside your home directory or under your home directory that ends with some kind of extension. Okay. So you first say enter an extension without the dot, maybe txt, tif, jpg, whatever you say. This will be read in extension. Okay. And then it gets a diagnostic message, okay, finding all files in your home area with this extension. Then what it will do, it will call ls-r tilde. So ls is list all files recursively, and the root directory is tilde, that is your home directory. So that will give you a listing of many files. Then I filter that through grep. Okay. So only the files that will be filtered will be, okay. Grep takes a regular expression, right? So this should be a regular expression. But at the same time, this is for the moment handled by the, I would say, shell. And there may be a small error here. I think there is a small error. I may have missed this backward slash dollar here. Okay, I will check. Possibly that is needed. Okay, so before calling this, what the shell will do, it will get the value of dollar extension. Whatever you give, it will simply replace this. And it will also try to evaluate something like dollar quote or something like that. So it should be escaped. Backward slash dollar should be there. So that shell takes it literally. Okay, I think so. Okay. So here what you are doing, ls-r is basically a shell command. You can write a similar thing in C. So there are some specific things, specific ways of handling entries of directories. But that requires a library and all that stuff. You need to know how to do it. Okay. But the shell is good at making file listing, recursive file listing. just same ls minus r tilde. Okay, then this shell script calls the specialist grep for doing the filter. Okay, and then you write it, and then you run it, change mode a plus x, all plus x, find all that essay and run it. And these are all the TIFF files that are there in my home directory, not home directory, home area. Okay, so this program, this shell program demonstrates how you can simplify your task. Okay, definitely you can write a C program for this. The C programs do exist for handling directory entries. But this is much simpler, right? A C program doing this will be at least 200, 300 lines long. Okay, but here you can manage in just some 4 or 5 lines. This is something at which Shell is good. And then this is what it is calling a specialist. Great. Happy?
Yes, sir.
So what is tilde and pipe doing?
What is tilde? Tilde is your home directory.
And pipe?
And pipe. Okay, whatever is output by this thing, this will be piped to this grep. Okay, so you just write that command ls minus r tilde. You will see list all the files recursively listed under your home directory, or not home directory, I mean the entire home area. Okay. And that listing will not be printed here, but it will be piped to grep. So that will be the input of grep. Whichever lines match this thing, this pattern, those will be only printed. Okay.
And sir, why is there a dollar after extn?
Yeah, this dollar I meant literally. What is the dollar in grep pattern? What does dollar stand for?
The end of the line.
End of the line. Okay. So I want this extension to be the last thing in this string. But if I have something, some file like maybe central image minus 1500.tif dot something gz, those things will not count. Those things will not be printed. Right?
Okay, sir.
Okay. Okay, any other question on this code? Oh, perhaps no. And since grep can handle regular expressions, you can enter an extension which is basically a regular expression. Okay. So for example, enter an extension dot. Okay. So I can simply say this A to Z. So what are the files that will match? So all single name extensions like .c, .s, .z and so on. Okay. And you can also enter extensions in this pattern. So A to Z, any number of times, followed by a non-alphabetic thing, digit or some other symbol. Okay. There you can see this is something. 7 tilde ending with 0, 2, 4 tilde 3. Okay. So since you are actually calling that, what is that called? Specialist grep, which specializes in handling regular expressions. So you can also supply regular expressions like this. Not only literal extensions. Okay. Now once again you think, if you want to do it in your C code, you have to use some kind of library, or you have to design these regular expression matchers yourself. Okay. Shell programming does it in just 5-6 lines. Okay. This is yet another example where you can use the specialist Gawk, okay, and run this way. Interactively, the user enters a database file, and these are the commands, Gawk commands, okay, and you simply pass this file, and this is the command. You can run Gawk this way, although we usually do not do it. Okay, you can do it. Ah, yes. Okay, so $1 and $2 have different meanings in Bash and Gawk. Agree or not? What is $1, $2 in Gawk?
So the first and second record. First and second heap of a record.
First and second records. And what is $1 and $2 in Bash?
The command line arguments.
Right. So here I have used a single quote. Okay. Inside single quote in a shell program, these dollars are not evaluated. They will simply go literally. So Gawk will take this $1 and $2 literally. But if I double quoted it, then $1 and $2 will be evaluated by Bash, whatever the value, if any, is there. This will be replaced here. Okay. So single quoting, since the comments of Gawk are written in single quote, Bash does not expand $1 and $2. So $1 and $2 will go literally to Gawk. Okay. And these are the results. And okay, here is another useful feature. These are called here documents. Okay. Echo minus n, same thing, read database file. Okay. Then what I do, whatever follows here, I simply cat this, type this, and store the result in a file called thero.awk. Okay, so whenever I say cat less than something, greater than, this is the redirection. This is not redirection because it is too less than. So what the Bash interpreter will do, it will keep on reading until it finds a line that has this end of text, end of whatever, end of program or whatever. Okay. But in this here documents, these dollars are actually expanded. This is similar to single quote, double quoting. Therefore, in order to make sure that this $1 and $2 go literally to the thero.awk without substitution, I have just used backslash this. Okay. Okay, so echo in place of cat does not work. You just figure out why. Here documents expand the variables. To prevent this from happening, you should escape this $, by backslashing it. Okay. And then you have written the file thero.awk, gawk minus f this file name, and then give the database file. Happy? And this is the result. Okay. Okay. Yeah, so what I have done here, I have simply printed this, but I could have stored this as in a variable, gawk output. Okay. So this is a here document. It creates this thero.awk, but instead of running it as a command, it runs it as a command, but whatever it produces as output, this will no longer be printed, but it will be stored in this variable gawk output. And then you can echo $gawk output. Okay. And actually this is something like this, but if you just quote it, then you will get this kind of listing, this kind of listing. Anyway, that has to do with this internal field separator and all that stuff. Let us not worry too much about that. This internal field separator issue, I do not want to deal with in this introductory set of slides. This is clear, right?
Yes, sir.
Okay. Now we will see a very interesting thing. A program or a function, shell function, returns a status. That status is stored in $? And I am suggesting that use those as status. Use that return value as status. But then whatever should go to std out, this is now stored in a variable. Okay. So you are simply running something like ./a.out with or without some command line parameters. Whatever the program is supposed to print, you can redirect it to a file. Here what the shell does, it is simply storing in a variable. This is a feature which is not easy to implement in C. Although it is doable, there is a way, okay, of redirecting std out to a string. Maybe you will learn all these things in your OS assignments. But this is a very natural thing for a shell program to do. Whatever a program outputs, prints, that entire thing can be stored in a variable. Okay, and we'll see the implications of this. Okay, and once you, this is yet another, I mean, there are too many examples of similar type. So here I am storing it. Okay, and since this is a local variable now, or I would say a shell variable now, okay, you can do any kind of processing on it. Okay, for example, I can figure out which are the theropod dinosaur whose names do not end with S. Okay, so these are the, so you once again filter it through grep. Okay, and this happens to be only these 6 names. Otherwise, you have a huge names, right? All these things, Albertosaurus, Megalosaurus, okay, Tyrannosaurus, almost everything ends with S. If it is not S, you can supply this pattern. Okay, X, X, R, 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 R. Okay, so let us now look at this thing. Return modes revisited. So how can a shell function or a shell code return something? Okay, but before doing that, let's say I need a small break. So this thing we will cover today, and maybe a little bit of conditions. The remaining things we will pick up in the next week. Okay, so let us wait for 5 minutes. I will come back. Okay, so I am back. And let us now look at this very important issue, and it would be going to be confusing. Let me make a, I would say, an advance warning. This is going to be very, very confusing because the return value is usually treated as a status, right? So you should not return things. Okay, so every command returns a value, and that is stored in $? Okay, and your shell functions are also commands, and the return value is to be treated as a status, and it is stored in $? And it is usually a small integer in the range 0 to 255. Okay. For so-called returning other things like larger integers, floating point values, strings, you have to use something else. Okay. This return value is not sufficient, and they are not to be used that way. Okay. Status should be treated as status, not as value. Okay. So how do you do it? Here is a list of ways you can do it. Set a global variable. Okay, and then you access the value of that global variable. Okay. You can return by echoing. You are not storing anything, but you are simply telling the user that this is the return value. You can simply echo it. So that but if you do it by this, then you possibly cannot immediately, I would say, process it. But then there is a way to store echoed things in global variables. But it has its own, I would say, pros and cons. Okay, so let us see how we can use these two types of return mechanisms. So for the moment, we will never use return to return things. Return will return only a status. Okay. Okay. So in this case, what I am doing, what is that? I am writing a function called hypotenuse that given side A and side B changes A to something like A square, changes B to B square, then stores something called C square to this A square plus B square. Okay. A and B are local variables. Okay. So whatever you do on A and B, it does not matter. This is not reflected outside, even if you have variables like A and B outside. Okay. And then what you do, echo, you pass it this square root of this through this BC. This is a kind of calculator. Okay. Floating point calculator. It will compute the square root, and you are storing that whatever is echoed by this BC, this calculator, to the global variable C, and then you can print C. C square, you see that this is also a global variable. Okay, because I have not declared it using local. Okay. Therefore, if I now print the value of A and B and C, so echo minus n, enter A and B, read A and B. Then you just call hypotenuse $A, $B, $A, whatever value is used. This is red. This will go as $1 here. The value of B will go as $2 here. Okay. And after this returns, this has already done two things. It has set C, it has set C square. These are global variables. So you can print these things after the call of the function, and you can see the correct things. A is 5, B is 6, C is something like 7.8 to 7.810, blah, 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 and C square is 5 square plus 6 square, which is 61. Okay, so this gives you one mechanism of returning certain one or more values, in this case C and C square, by setting global variables. Happy?
Yes, sir.
Okay, so this is one way of doing it. Okay, and instead of setting C and C square, then you can simply I would say, yes, this thing now computes the C square, okay, and instead of setting C to a value, it simply equals this. So that 7.8102496759 is not setting any variable here. Okay. Instead, it is simply equal. And outside, you, as earlier, read A and B. Then here you set the variable C. Whatever is echoed by this function call, this value will now, the string will now set the value of C. So now if you print A equal to $A, B equal to $B, C equal to $C, this will be the result. Happy or not?
If it didn't use the single quotes, then it would have set C to 0.
What? This one, this code.
Yes, sir.
If that is, there are three types of code, right? One possibility is forward code, where it will simply set C to hypotenuse $A, $B, that literal string. If it is double quote, then what will happen? $A and $B will be expanded. It has the value 5 and 6, so C will get the value hypotenuse 5, 6.
If you don't write any quotes at all,
Then that will be, I would say, a syntax error, because C equal to hypotenuse, C will get this value, but then what is $A, 5, 6? That will be a syntax error. Bash will complain.
okay, sir.
Okay. So whatever is printed by your function or by some other comment, the function is like a comment, okay, that text, whatever is supposed to be printed, this will now set the variable C. So this is another way of returning things. Okay. But one thing I did not do here, I did not print C square here. So what happens to C square? Does it still get the value 61? Let us see. Okay, so let us say I initialize C square to something like not yet computed to this string, and I exactly call C equal to hypotenuse AB with backward quotes, and then I echo this A equal to $A 5, 6, 7.81 whatever, C square equal to, I print the value. It still prints this thing. So it does not get the value 61 as you expect. Do you have any idea why this is happening? I think I have told this in the last class, but I didn't.
Sir, it is executing hypotenuse as a command, so it will open in another shell.
Yes, exactly. So this shell program opens a sub shell to execute this command. So whatever happens in that sub shell is not reflected when once again you come back to this original shell. That is the reason the value of c squared does not change. And of course, if I declare the c square as with the minus x parameter export, then this will go there, and I think I didn't do it, even I would say, I didn't experiment with this. If you export this, if you make a change in the sub shell, is it still reflected in the outer shell? We have to experiment. I do not give you a ready-made solution, but anyway, I have not exported any variable here. A, B, C, C square, these are all relevant apparently to the current shell. Okay, so that is the way, that is the reason why C square value does not change. This opens a sub shell, and inside that shell, sub shell, C square is assigned some value. So in the original shell, the value of C square is not modified. This has huge implications. Okay, so what happened to C square? So this is the reason. Whenever you run a command using this or this, is another syntax, same thing. Sub shell is opened. A function call also works like a command. Okay, and any changes in the global variables of this shell that you make in the sub shell have no effect in this shell. Okay, so that's the reason. Oh, this happens even if you export your variables. I see. Okay, then I have done it. Okay. Okay, any change you do on some global variables of this shell in a sub shell, these changes do not have effect in the current shell, even if these variables are marked as exportable. Okay. And that is the difference between this. Just running the command in this shell, and here I'm running this. Okay, so I'm running this command in this shell. Here I am running this command, the same thing I am running, but in a subshell. Both will echo the same thing. Whatever is echoed by this is stored here, and then you are simply echoing it. Output is apparently the same, whatever you see, but there is a difference. Understand? Okay, in the first case, command is executed in this shell, whereas in the second case, it is executed in a subshell. Confusing or clear?
Yes.
Clear, great. Okay. Okay. Okay, so okay. So there is another example I will take up later. Now let us look a little bit on this logical constructs. Okay. At if then else and looping, these things we will study in the next class, but today, since we have a little bit of time, I don't want to go beyond 4 o'clock, but anyway. So we can just look at the logical conditions. Okay. A while loop, or and conditional statement like if or if then else, those things require some conditions, right? Logical conditions. So what are logical conditions? How to write those, the syntaxes, these things, let us see. Okay. Okay, so it's definitely needed for conditional execution of blocks and also in loops. And unlike C, 0 always means true, and non-zero, any non-zero value means false. Okay, so it's basically the status. Okay, command returns a status. This is where I am actually using that return value. Okay, the return status indicates true or false. Okay, if it is 0, it implies successful completion of that command. And if it is something non-zero, it implies unsuccessful completion of that command. So this is the shell convention. Okay. And immediately after that command completes, you can get that return status in that variable $? And these different conditions can be logically joined by this or and negated by this bang, like in C. And you can use this parenthesis for disambiguation if needed, but then you have to understand clearly the precedence rules. And why I did write other types of conditions? Oh, okay, fine. So this is one type of condition, right? The condition checked by the return status of a comment, and functions also run like comments. Okay, but we typically want to compare numeric values. We need to compare strings, and there is another type of condition that is based upon file attributes. So whether a file is readable, whether a file is a directory, that kind of stuff. Whether a file has execute permission, that kind of stuff. And all these things can be done. Okay. And this type of conditions can be checked using this syntax. Test condition, or this is, I believe, a little bit more, I would say, convenient for me. Okay. Inside a pair of square brackets, we put the condition. Okay, and that condition may be this kind of thing. Okay, or even this kind of condition. Okay, so let us see an example or many examples. And note the space after this and before this. That is needed. Okay. Follow this. Okay. This is another important thing, so I will explain these things. These are short circuit operators, which means what? I will just take. So let's say in my user directory, my home directory is a home folder, and I am checking whether there is any file with a single letter name followed by dot, followed by some star, anything. Okay, and it turns out in the foobar's home directory there is no such file. Something like a.txt, b.c, there is no such file. Okay, and you recall that the star is expanded by the shell. It does not find any match. Therefore, it passes it on literally to ls. ls again takes it literally. It does not try to expand star. Okay. So it just tries to find out a file with this name, starting with a opening bracket, A minus Z. This is just literal string, a file of this name. It does not find it. So it prints it, no such file or directory, and therefore, basically this ls command fails. Okay. And it returns some non-zero status. That is echoed by this $? This is 2. Happy? On the other hand, there are 3 files with a single letter extension. This is assignment1.c, assignment2.c, and assignment3.c. So if you now do this, tilde start.this, then the shell makes this, I would say, substitution. These 3 files match, so it simply says this, this, and this. Then calls ls. Ls will simply print these things. And then if you echo $? You will get 0 because ls now did not fail. These files are there and therefore it printed these things. Therefore it succeeds and returns 0. Happy? How you can get the exit status using $? Okay, so in the rest of this thing, I will explain this concept, short circuit operators. So I do this, and then I do this, then echo $? Okay. Now this command fails because this fails. And this is an AND statement. This is evaluated from left to right. Because this is already false, there is no reason why the second thing should be executed. Because this is an AND statement, one value is already proved to be false. Therefore, it simply returns 2. This is not executed at all. And that is quite similar to C. If you have an AND statement, this thing is already false, there is no need to evaluate this thing. Because the result is anyway going to be false. That is why you do not see this listing. But if you separate these things by this, then the first thing fails. Okay, so ls returns 2. But since this is an OR statement, there is a possibility that the second one is true. So this will now be evaluated. So ls will do something like this, and the eventual exit status is false or true, which is true. That is 0. Understand the concept of short circuit operators, right? The conditions are evaluated from left to right. Okay. And evaluation will stop as soon as the final outcome is determined. And this is the way you can use NOT. This one is false. 2, NOT of 2 is 0. Okay, you can go through these remaining examples to understand more about this. And now let us look at other types of comparisons, like numeric comparisons. Okay, so syntax is expression 1, then comparison operator, followed by expression 2. Okay, so here are some. Okay, so examples are there anyway. The numeric comparisons apply only to integer values. And if use of fractional or non-numeric or undefined values lead to errors. And yeah, so here are something. So this operator said expression 1, this is true if and only if expression 1 and expression 2 evaluate to the same value, same integer value. So similarly, you have not equal, any, less than equal to, greater than, and greater than equal to. Okay. Happy? So here are some examples. X equal to 3, y equal to 4, z equal to 5. Now, okay. I mentioned you that you should give a space between after this and before this. Otherwise, it is treated as a comment. It says not found, and it returns something like 127. Okay. Here also, a space is necessary. Okay. Because there is some problem with this too. But if I now make it syntactically correct, and I check whether $y is equal to 3, the result is false, right? 4 is not equal to 3. So the question mark is 1. $y is greater than x. What is $y? $y is 4. X is what? 3. $x is 3. 4 is greater than 3. Yes, it is true. So 0. Happy? And you go through the remaining things. And here is a more complicated thing. You are checking whether x square plus y square is equal to z square. But this is a Pythagorean triple. So 3 square plus 4 square is 5 square. So the answer is true. Okay. And this last example demonstrates that these values should evaluate to integers. So if I compute the square root of 10, I think this is 10. No, scale is 10. What is z? Z is 5. So square root of 5 is 2.2360 whatever. And I am comparing that with x, but this is not a numeric, an integer value. So Bash complains, so this is not an integer expression, and return something. Okay. Returns 2, which is false. Okay. And string comparisons, of course, yeah, strings can be compared for equality or inequality. Okay. Equality is just equality. Or you can use equal to. Okay. Once again, you see that there should be a space here. Otherwise, this is interpreted as variable assignment. Okay. Not equal to. And there are some special things. True if the string is 0. Okay. It's the empty string, epsilon. Non-empty, not epsilon. And here are some examples. X is this, y is this. And you say $x equal to $y because there is a space here. There is a problem. Therefore, Bash complains too many arguments inside this. It returns something. But if I quote it, this is fine. They are not equal. So this is 1. And if I negate the comparison result, this is 0, and so on. Okay, so you go through the remaining examples. Happy?
Sir, why does it say too many arguments?
$x evaluates to full on, $y evaluates to full on space Barik. So what is here? Full on equal to full on space Barik. So
Okay,
Barik
so
is the third
space is
argument.
again.
right? Because of the space,
Yes.
this is treated as a separate argument.
Sir,
Yeah, tell.
what is happening in the last one? The last one.
This one.
Yes, sir.
Yeah, what is the problem?
Like, what is the effect of that space then? Like,
Okay. Okay, so this 1 second says if I quote this, okay, then this is treated as a string with two spaces. So it is not the zero string. So it is a string space. So this is not a zero string, therefore 1 is returned. 1 is false. If I do not code this space will be part of the syntax of this. So what this sees after this is an empty string. Therefore, it returns true.
if we do not, if we just say minus z and then we do not say anything, what would happen?
Like this. Whatever happens here, this will happen like this.
Okay, so writing only minus z will give an output of
This
0.
is equivalent to this. Exactly.
Okay,
Okay.
sir.
Be careful about spaces.
Okay, sir.
So far, while writing C codes or Gawk codes, we were pretty fussy about spaces. There may be space, there may be no space. Here, spaces are very important. Okay. Okay, and finally, some conditions based on file attributes. Okay, I think I should have, like this, should have the spaces here, which I did not write here. This is not good. So this space minus E file space this. Okay, I will correct this errors. So this is true if the file exists. This is true minus F if file exists and is a regular file. Okay, this is file exists and is non-empty. Minus D, which is file exists and is a directory. File exists and has read permission, write permission, execute permission. And this two operators, newer than and older than. Okay, every file has some timestamp, right? Based upon the timestamp, whether it says that file 1 is updated later than file 2 or not. If it is later than this, then this is newer than. And if it is older than this, that means it is updated earlier than file 2. Okay, so here are some things, but this is not an exhaustive list. But you can find exhaustive all file-based comparisons in some books or other material. Okay. Okay, so here is a small example. Okay. I run this with a command line argument, which should be a file name or a directory name. And this program will give you the status of that. Okay, so if $hash is equal to 0, that is if you run without any command line argument, then $hash is 0, then this is false. Sorry, this is true. If $hash is equal to 0, this is true. And if this is true, this is a short circuit operator. So the second has to be evaluated. So you echo this and simply exit 1. Do not come to the remaining things. On the other hand, if $hash is greater than 0, that means you have supplied one or more command line arguments. Then this is false. Then there is no need to execute this. So come to the next thing. Okay. And once again you check whether the file exists. Now here I have something $1. If $1 is not there, I would not have come here. So $1 is something. And if that does not exist, then this is true. So this is evaluated. And you simply say this does not exist and exit 0 maybe. Okay. And if it exists, then this is false. So this is no longer evaluated. So you come here. Happy? And you simply print that this file exists. And then you keep on doing this. If it is a regular file, you say it is a regular file. If it is not a regular file, just print it is not a regular file. If it is a directory, print this. If it is not a directory, print this. And then you use the permissions. If it is read, just say read permission is there. This write permission is there. Echo it, and eventually give a line break. Okay, so let's see. So if I just run this, it will say run with a command line argument, and $question mark is 1 because I have been here I have exited with 1, status 1. Anyway, I didn't print it. So if I give this argument, it says it exists, it is a regular file, it is not a directory, and the permission is read, write, execute, all the permissions are there. Likewise, if I call it on user, /user, okay, this is a directory basically, exists, it's not a regular file, it is a directory, you have only read and execute permission. Okay. Likewise, device null is a device. It has only read write permission. It is neither a regular file nor a directory. It is basically a device. Okay. And etc password exists. It is a regular file, not a directory, and you only have read permission. Okay. Now let us look at this. Tilde / special SPL, I mean not special, systems programming laboratory /star. Okay. This example actually illustrates that before calling this, okay, the shell expands this to all the matches. And this shell program looks only at $1. That happens to be the ASCN, which is a directory. It is not a regular file, it exists, is a directory, and it has read, write, execute permission. What happens to the other matches? They are actually ignored here. This works only on $1. Happy?
Yes, sir.
Good. Okay. And then this is just a little bit of things. If I have normal Boolean arithmetic, AB plus C is evaluated as AB plus C. This will evaluate to 2, true. But if I interpret it as AB plus C, it will be something like this. Okay. So the question is, what does the shell do? In a normal Boolean expression, this product operation, that is the AND operation, has larger precedence than the OR operation. But in Bash, this AND and OR have the same precedence. So they are like star and slash in arithmetic expressions. So it's basically evaluated from left to right. Okay, left to right associativity is used for disambiguation. So A plus BC is interpreted in the shell not as A plus BC, but as A plus BC. Don't forget this. This and this have the same precedence. So left to right associativity is used for disambiguation. So this is interpreted as A plus B whole and C. Happy? So if you imply A plus BC, then use parenthesis like this. Okay, it can be done, but you have to use this extra parenthesis. So here are some example, and I believe you can figure it out. And of course, you also remember the true and false, this kind of things we will use in loops and conditions. This true always evaluates to true, false always evaluates to false. So these are the keywords. Okay. Okay, so I think I stop here. So remaining things, conditional statements and loops, we will study in the next class. That will be all the things that we wanted to cover. Okay, so let me know if you have any immediate questions. The shell syntax is quite different, right? You have to learn it. Okay. So if there are no more questions, it's already a 2-hour session. Let us stop.
Thank you, sir. Thank you,
Okay.
sir.
Thank you, sir.
Thank you, sir.